Hello everyone, I'm Alyn Rockwood. It's my pleasure to welcome you to our course on geometric algebra and the mathematics programming language GALLOP, which is specifically developed for geometric algebra. I will do the introductions on the algebra itself, and Dietmar will concentrate on GALLOP, which is what he is the main person behind the development and applications of GALLOP, particularly with projective geometric algebra and with conformal geometric algebra. So let's begin. I start this with a crop circle from 2000. Back then I was quite interested in these objects. And, you know, whether you believe Alex and Floyd made them or aliens, the interesting thing about them is they are made completely from a few conformal transformations, reflections, translations, and rotations, etc. When we get to the end of this presentation, I hope you'll understand why I just brought that up. This will be a linguistic introduction. I'm going to treat geometric algebra as a language, as mathematics is. Now, Galileo believed that that mathematics is the language which God wrote the universe. I'm not so sure about this, but I certainly believe that mathematics is one of the important languages by which we understand the universe. I'm going to make this assertion. The most significant advance in mathematics is syntax and not method. You're welcome to disagree with me, but I'm going to make a case for it right now, and it has implications for geometric algebra. I mean, the first case is to think of Roman numerals. I mean, there's a grammar that is very clumsy, does not suggest how the mathematics is done, whereas Arabic numerals do. Here's an example of how mathematics was done in 1550. This is a very simple formula that Cardano was describing, and I could give you a while and you could probably figure out what that formula is. This is how mathematicians of that age actually did mathematics. About 1600, Vieta abbreviated a lot of this. He introduced the idea of concatenation to multiply and certain Latin phrases for exponentiation, as well as equals and some of these others. So if you know a little Latin, this is much easier to read as far as the formula goes. By 1650, however, they had introduced the plus and the minus and the equal signs, and suddenly what Cardano was thinking is very obvious to the modern reader, what needs to be done. So without this sort of advance in mathematics, in the language of mathematics, I highly doubt that techniques like the calculus of Newton and Leibniz would have developed. Can you really believe that if Newton had to do it and explain everything the way Cardano did, that calculus would exist today? That's my assertion, anyway. The best mathematicians are linguists. I mean, quite literally. Günter Grassmann, who in a lot of ways is our pioneer in geometric algebra, was best known in his own lifetime for translating Sanskrit and producing a dictionary of 10,000 or 2,000 words of Sanskrit. But what Grassmann was really good at was how to formulate a language to capture the mathematical concepts he had in mind. And if we view this again as a language, we're going to start with adjectives, not the nouns of the language, because we need to describe the nouns. And geometric algebra, we're going to start with magnitude, and this is, you know, can be length or area or charge of a particle. we're going to talk about the orientation in space. Now, if you think of vectors, there's a two-dimensional orientation in space. But we're going to have more general nouns. So it might be a plane, might be three-dimensional, and that sits in a larger space, and that's its orientation. Grade is its intrinsic dimension. So again, a vector is a one-dimensional object, a plane is two-dimensional, and so forth. And then finally, we're going to assign a sense, up or down, left or right, plus or minus. All of these are specific applications of our sense. If we think of putting sense and orientation together, they give us the familiar direction, like the direction of a vector. Our nouns are k-vectors. Okay, you know what a scalar is, you know what a vector is. A bivector is more like a vector, but it's a plane. Its grade is two-dimensional. This is not two vectors. This is a noun of our new language. It's a bivector. You have to kind of make this jump like you made the jump from scalar arithmetic to vector algebra. Really understanding what a vector was, something which had direction and magnitude and was not a fixed point in space. A bivector is very similar. Trivector, k-vector are just higher grade elements. Then we have what we call a multivector, which is just the sum of k-vectors. So we're going to be able to add all of these different grade vectors together. If you're asking yourself, how do I add two different grade objects together, different dimension objects, it's a good question. We'll come to it. Then we're going to have the verbs. The verbs are binary operations, what you're familiar to. Multiply, addition, subtraction, divide. Those sorts of operations need a definition. They need to be able to operate on our nouns, on the k-vectors and multivectors. This is the sort of thing that Grossman excelled at. He looked at all of the concepts he wanted to incorporate into an algebra for geometry, and he assigned them different verbs, different operators. And he did this extensively in his books. So the mathematical method, which was really pioneered by Euclid, but really extended by Grossman to many dimensions, consists of the following. We consider the language that we need to describe the semantics of what we want, whether it's geometry or physics. I think I want two vectors to describe the area. I'm going to call that a multiply. It's the sort of thing that Grossman went through. Then we check for consistency. Do we have any contradictions in all of these sentences that I've put down? And then the last step is to look at all of the sentences which describe my algebra, and I minimize that to a set of axioms. I look at it and say, these two sentences imply this one. I can get rid of these two and call this one an axiom. Well, this is a combinatorial effort, and this is really where people like Grossman excelled as mathematicians. What is my minimal set of axioms that will produce all of the properties I want for a good geometry? William Kingdon Clifford came along and he produced another element of our language. I call it the preposition. We can take two elements of two nouns of our language and add them together even if they're not the same grade, if they're different dimensions. And we're going to define something called the geometric product as a summation of the dot product, which is a scalar, by the way, if A and B are vectors, and the wedge product, the outer product, which is a bivector if A and B are vectors. And you think, how can I add a scalar to a bivector? Well, it isn't really a verb. We're not producing a new result. We're just placeholding them in the algebra. You've seen this, by the way, in complex analysis. You don't really add a real number to an imaginary number. You just use it as a placeholder. As long as it's consistent in the algebra, it works. The same for geometric algebra. So once again, we have this addition, which is maintaining the dot product and the bivector when we multiply two vectors together, A and B. We're going to generalize this to all of the vectors, the k vectors. But first, I'd like you to stop and think for a second, by way of motivation of why this is a good product. What can two vectors do? What can they really represent? If you think about that deeply. First of all, two vectors, we know one can project onto the other. It's a dot product, right? So the projection of one vector on the other can be captured by a dot product. The other thing is, of course, two vectors define a plane in space. So we have defined the wedge product. From two vectors, we can define the plane going through those two vectors. I ask you to find some other property that two vectors can show us. Maybe you can, but basically that's it. Now this, probably at this stage, this geometric product that we're defining may seem a little strange to you, but I claim the fact that this product encapsulates these two properties is fundamental and very deep. And in fact, when we get into the axioms, the geometric product will be foundational. That will be the product we define. The dot and the wedge products will be a result of our geometric product. So here are the axioms. All of our k vectors and multivectors form a non-commutative algebra. Think of matrix algebra. Matrices are the same. We can't commute them, but everything else, distributive, associative, etc., that's a matrix algebra. So our geometric algebra is also a non-commutative algebra in its multiply like matrices. Here are the really distinctive axioms, and it's amazing that we only have 3 of them. First of all, scalar multiplication commutes with our elements. Of course, that is also true of matrix algebra, but this is worth specifying. Number 3, for any vector, just a vector, its square greater than 0 is a scalar, greater than or equal to 0. And finally, the really distinctive axiom, we're going to define A dot A sub k, where A is a k minus 1 vector, and A wedge A sub k is a k plus 1 vector. So we're going to define them in terms of the geometric product. So A dot A sub k is equal to 1/2 A times A sub k minus, and then alternating based on the k, AK A. The wedge just has the other alternation. And that really is the set of axioms that are going to give us all this rich language for geometry. There is one more axiom. If the space we're working in is k-dimensional, then we want the wedge of any element with A sub k equal to 0. This is just a bookkeeping thing. We don't want graded objects higher than the dimension of our space. So, as a mathematician, I find this amazing. As we get into the implications of geometric algebra, and you think back, this is the set of axioms, how did Grossman and Clifford come up with this? So a little diversion into history. Before Clifford was working on this, William Hamilton was developing quaternions. People in the mid-19th century had this great need because of physics and electromagnetism, to be able to describe 3 dimensions and higher dimensions. Hamilton did that with quaternions. Of course, he was just looking at the completion of an algebraic set, trying to generalize complex numbers. But he also came up with a way of dealing with higher dimensional objects. At the same time, or a little later, Josiah Gibbs and Oliver Heaviside, working in parallel, thinking about this, decided that all that was needed to really describe a 3-dimensional physics was scalars and vectors. I can describe a plane as a cross product of 2 vectors. I don't need the plane. Occam's razor, right? We don't need that extra graded object. And so Gibbs and Heaviside developed this idea of vector analysis. So here is one of the applications of quaternions at the time. Maxwell did not have vector analysis. He described his Maxwell's equations in terms of quaternions. If you really want to have a fun time, go back and look at the original 20 Maxwell equations described in quaternions. It's actually surmised that the 4 Maxwell equations that were derived much later than Maxwell waited upon vector analysis to do that. So, why did vector analysis, as we know it, win out over geometric algebra? First of all, Gibbs proposed the cross product, which solved the problem in 3 dimensions. Gibbs was a thermodynamicist, and for him, 3 dimensions was enough. He wasn't thinking higher. His student, Wilson, published a very famous book, Vector Analysis, that everybody used and was perhaps the greatest PR piece that vector analysis had at the time. And unfortunately, Clifford died very young at age 33. So he wasn't around to pursue applications and to proselyte for his ideas. Let's look at some of these applications. In geometric algebra, and I'm talking about the geometric product here, vectors have an inverse. I mean, every beginning student in vector analysis at some stage or another has tried to divide by the vector and then found out they couldn't do it. In geometric algebra with the geometric product, you have an inverse and you can basically divide by it. It has a very strong geometric meaning. It basically takes any vector and inverts that over the unit circle. Same direction, just changes the magnitude. Do keep in mind it's non-commutative though. That's one of the primary mistakes that beginners make, is to commute this inverse. The other thing is I can take any equation that I have with multivectors and break that into separate equations, one for each grade. What I represent here with the angle brackets and the subscript is the grade of that k vector v, or multivector v. And so I get a separate equation for each grade in my multivector equation. This is like complex analysis. You get 2 equations for every equation in complex variables. It's very useful, by the way. Here's another very nice property of geometric algebra. If I take the original vector x and I want to reflect it by a vector a, I simply have this sandwich operation, which we're going to see a lot of, by the way, where I take A inverse, we know what that is now, I multiply it by my vector x, and then multiply it by A. If I take the negative of that, well, that's just the reflection of x. So reflections are nice. Once I have reflections, this is far more complex than it needs to be. 2 reflections, the reflection of this through the plane, where A lies in the plane, reflection of this, and then the reflection through B gives me a rotation. B inverse, A inverse X, A, B. That's how I rotate a vector around the normal of a plane. So you can really look at BA times BA inverse as being a rotor. Here's another really nice thing, drops out just from the definitions. I'm going to define, just pure definition, a bivector Z as the geometric product of A and B. We know that's A dot B and A wedge B added together. And we're going to define Z reverse, or V conjugate, as BA, just the commute of that. Now, since from definition we know A dot B is this, we can call this 1/2 Z plus Z conjugate. Well, you know where it's headed, right? Just I'm going to define the real part of Z as lambda cosine theta. The theta and the lambda come out by definition. And A wedge B is going to be Z minus Z conjugate. Well, that's the imaginary part. And then if I put them together, Z is equal to lambda cosine theta plus I sine theta. I here is the unit bivector. I should have mentioned that earlier, because here we have the bivector definition, right? So I have to have the bivector there. We have suddenly, at our fingertips, all of complex analysis. It's a special case of geometric algebra. There's a very nice duality in geometric algebra. We're going to let sigma 1, 2, and 3 be orthonormal basis vectors, a 3D space, for instance. And we have now a basis for the geometric algebra. We have the scalar 1, we have the 3 unit vectors, we have the 3 bivectors. This is the 3 different ways you can combine the vector bases as bivectors, and then we have the 1 trivector. So altogether we have 8 elements in our basis, right? And in general, if my basis is n, I have 2 to the n basis elements for my geometric algebra. So if we now look, and just from the definitions of the geometric product, look at something like sigma 1, sigma 2, sigma 3 squared, that's our unit vector, because these are unit basis elements, squared. But if you do the algebra, you find out that's -1. In other words, I, the pseudoscalar squared, is -1. And this is true in any dimension, not just for complex numbers. I times sigma 1 gives me the bivector, which is dual and also perpendicular to the vector. And likewise for the others. So we get these nice relationships, this duality relationship between the bivector and its dual, which is perpendicular. Kind of like the cross product, right? So in general, here's how the duality works. We have scalar, vector, bivector, trivector, etc., up to n-1 vector, and the n vector. Well, the n vector is our pseudoscalar. And it acts, if you look at it completely abstractly, it acts like the scalar. You have this complete dual structure between the pseudoscalar and the scalar, the vector and the n-1 vector. That's quite a useful property too. And immediately again, if I define I as a special bivector, unit bivector, as sigma 2, sigma 3, j as minus sigma 3, sigma 1, and k as sigma 1 and sigma 2, I'm going to get the quaternions and say, well, why do I define it in this way? Well, if I define it in this way and multiply these things out with the geometric product, I get the following identities. I squared equals j squared equals k squared equals minus 1, and ijk equals minus 1. These were Hamilton's equations for quaternions. So conceptually, instead of looking at a quaternion as a scalar and then kind of a vector that we squish together and then we give them a whole bunch of axioms to multiply them together, we think of it simply as a general rotor in geometric algebra, where our I, j, and k are vectors. They rotate. They rotate planes into duals, and they rotate duals into planes, into bivectors. So it's a much stronger concept for quaternions than I think what we were taught. Vector algebra, also a special case, Gibbs vector algebra, we can define the cross product simply as a pseudovector times a wedge b. Remember again, a wedge b is our bivector going through a and b. Our pseudoscalar times that gives us this dual, which is perpendicular to the plane defined by a wedge b. So with the wedge product, which only goes to, with the wedge product, we get our cross product. The cross product only works in 3 dimensions. The wedge product we can generalize. And finally, just looking at spherical geometry, because it is so sweet, we're going to define a bivector A by b times c. We've got these 2 vectors, b and c. Another bivector c times a. That's here. There's a. And we're asked the question, what is a times b? What's the new bivector c? Well, we're just going to do our geometric algebra. A is b times c. B is c times a. C times c, remember they're unit vectors, becomes 1. We get ba. So in spherical geometry, if we multiply this great circle by this great circle, or any wedge, any bivector of those great circles together, we get the great circle, which is connecting B and A. Instead of BC, CA, we get AB. So basically, geometric algebra is a better, more comprehensive language. It just captures more, it does more, and it's more intuitive for geometry. If you want to look at the course notes, you can study this family tree for geometric algebra. I'm not going to take the time to do it now, but for the die-hard mathematicians in the group, it's pretty interesting to see how it developed from all of these influences. Anyway, to summarize, geometric algebra is unifying. This geometric product compacts all of our knowledge. You know, I'm putting together complex quaternions, vector algebra, and many other algebras, Cartan's tensor algebra, the exterior algebra. So, you know, I keep thinking, if I were young and in high school, I had learned geometric algebra, how much time I could have saved not having to learn all these separate algebras and then translating between them. The one I'm thinking of in particular is quaternions. I used to do Euler angles and had all the problems, gimbal lock and collapsing. And, oh yeah, I got to go to quaternions. Oh, okay. How does this work? Well, here's how you translate. Here's how you multiply. If I had learned geometric algebra, it would have all been there. It's intuitive geometrically. That's how Grossman defined it, and Clifford continued it. It's very efficient from a process of thinking about it. As far as actually computing the efficiency, that's what Dietmar is going to talk about coming up here. It's coordinate free. I snuck this in on you, okay? Nothing we did here has coordinates. And you might say, how do you do coordinates without, how do you do geometry without coordinates? Well, you know, I can take any object and I can define its shape without coordinates. I just need to know, like, the corners. What's the distance between the corners? What's the angle between the corners? Those constraints will completely define this guy, and it doesn't matter how it sits with respect to a frame of reference. That frame of reference is actually redundant. Until you need a frame of reference, like you're going to draw something on a computer screen, you really don't need coordinates. It has separation of parts, very nice for solving equation, and it's dimensionally fluid. We talked a lot about 3 dimensions, but when you get into higher dimensions, it really is the same algebra. Try doing this. I mean, you physicists out there, you know what happens when you go to higher dimensions and you don't have a cross product anymore. So with that, I'm going to turn it over to Dietmar to talk a little bit about how you actually compute and deal with these in a computer language. Dietmar.
Welcome to my presentation, Introduction to Gallop and Projective Geometric Algebra, PGA. The main reference to Gallop in general is my book, Foundations of Geometric Algebra Computing from 2013. Its new online version, Gallop Web, is described in my new book, The Power of Geometric Algebra Computing from this year. So what is Gallop in general? Its standalone version is a software in order to visualize geometric algebra, in order to compute with geometric algebras of arbitrary dimension, signature, and the main reason to work with Gallop is to generate optimized source code from geometric algebra algorithms. The software is freely downloadable from gallop.de, and it is also an open source software on GitHub. This is the principal architecture of Gallop. At the top, you have your application. Then parts of the application can be described based on geometric algebra. You write your geometric algebra algorithm in a specific language. Gallop symbolically optimizes this code to your preferred programming language, and many different computing devices can be used then. Here you can see the architecture in more detail. The geometric algebra algorithms as part of your application can be written in the so-called Gallop script notation. Then Gallop is generating based on symbolic computations an intermediate language. Here is it called GAP, Geometric Algebra Parallelization Programs. Then, depending on this intermediate language, you can derive source code for your preferred programming language, as for example C, C++, C++M, Java, OpenCL, Gapco, MATLAB, Python, whatever. And then you can use computing devices depending on the programming languages, for instance, PC, tablet, smartphone, GPU, DSP, FPGA, SoC, or even HPC. There are many tools for computing with geometric algebra, and the question is Gallop just another geometric algebra tool, or do we have some specific advantages? The big advantage of Gallop is that it pre-computes a lot before runtime. Means during runtime only a small part of computation have to be done, and sometimes it is really the case that, let's say, 90% of the computations are already done by Gallop, and only 10% are needed then at runtime. So why can code generated by Gallop be very fast? We have a two stages optimization in Gallop. The first is to optimize one product of two multivectors, and we also have an additional stage in order to optimize parts of algorithms, including many products of multivectors. For this stage, if you would like to use it, Maxima has to be installed. Gallop Web is our new online version of Gallop. It is a web interface in order to generate source codes also for various programming languages. And also, as with Gallop, the focus is on runtime performance, robustness, and numerical stability. There is a possibility of visualization using the Ganja software package of Stephen Decanic. And the main advantages of Gallop Web are that no installation is needed for this browser solution. And since it is a browser solution, many different devices can be used in order to work with Gallop Web. These are the main programming languages of Gallop Web. You can use and generate code for C, C++, or for Python, MATLAB, Mathematica, Julia, Rust. You are even able to generate LaTeX code for presentations of the results of Gallop, or directly generate code for this intermediate language GAP, which I already mentioned. These are the geometric algebras Gallop Web is currently able to handle. 3D projective geometric algebra is the default one. There is also a 2D version of it. And we will work with them next. And there are also extensions of these algebras, the compass ruler algebra and the conformal geometric algebra, which we also will get to know today in our course, as well as some high-dimensional geometric algebras, which we also will handle, especially the geometric algebra for conics and the double conformal geometric algebra. I already mentioned that Ganja is used by Gallop Web in order to visualize the results of the geometric algebra algorithms. Ganja is a software package written in JavaScript by Stephen Decanic. And here you can see the link to this software together with a link to the so-called coffee shop. A coffee shop in order to present some examples of different geometric algebras. A very nice tool in order to play around with geometric algebra and to get some experience with it. This is the main screen of Gallop Web. At the top you can see that the 3D projective geometric algebra was chosen. Then you have the possibility to choose the output type, means are you interested in code and visualization, or only in visualization, only in the generation of some code. Then you can see an area in order to describe your algorithm. It is called code to optimize. And if you are only interested in the generation of code, that's all. But if you're also interested in the visualization of your geometric algebra algorithm, then you can also use the two additional areas. One is for the assignment of concrete values to variables, and the other one is to specify the multivectors to be visualized, means which multivectors should be visualized and in which color. On the left side of the screen, there is also some additional help information. This is, for instance, for the conformal geometric algebra with some quick help about the representation of the different geometric objects to be used in CGA, and also some sample Gallop scripts in order to compute, for instance, the center of a sphere defined by 4 points, or for the intersection of 3 spheres. And additional information is the gallopscript.pdf, which you can download in order to get some information how to handle Gallop script, how to handle Gallop. Let's come to PGA now, to projective geometric algebra. Here are some resources. The first one is the Gallop web pages, means gallop.de is mainly for downloading Gallop and giving some information about it. And the next link is the link to Gallop web in order to use Gallop online in the browser. Then a very important PGA resource is the bivector homepage maintained by Stephen de Koninck. It includes many tutorials, documents, and cheat sheets and so on. And also one very interesting resource that you can also find on the bivector homepage is the PGA tutorial of Leo Dorst and Stephen de Koninck from the SIGGRAPH conference last year, which you can also find on YouTube. Here are some documents dealing with PGA, which you can also find on the bivector.net homepage. For instance, the geometric algebra for computer graphics course notes of the SIGGRAPH 2019 by Charles Gunn. Then a guided tour to the plane-based geometric algebra PGA by Leo Dorst. And a recent document about physics and how you can handle it with PGA. It is called May the Fog Be With You from Leo Dorst and Stephen de Koninck. Documents which are very important for developers are the PGA cheat sheets that you can also find on the bivector.net page. They are part of the SIGGRAPH 2019 course notes. And the nice thing for developers is that on one page they can find mainly everything they need to develop their applications. In this case, for the 3D projective geometric algebra, its basics, operators, how to deal with geometry, and so on. This is the structure of the 3D PGA according to the 3D PGA cheat sheet. We can see that this algebra in principle is 4-dimensional, means we have 4 basis vectors, E0, E1, E2, and E3. And then we have 2 to the power of 4, means 16 basis elements. And additionally to the vectors, we have the scalar, we have 6 bivectors, E0, 1, and so on. For trivectors E0 to 1 and so on, and one pseudoscalar. And the general multivector is just a linear combination of some of these basic elements. Let's come finally to the geometric objects, which can be handled in 3D PGA. They are mainly the planes, lines, and points arbitrary in space. For instance, the plane can simply be defined based on the normal vector and the distance to the origin, and the expression for it is normal vector minus d times E0. The line can be defined or represented based on the outer product of two planes, because the outer product describes the intersection of geometric objects, and this is why the intersection of two planes can represent a line, and a point can be represented as the outer product of three planes. This is the representation 1, the main representation, but later on we will also see another representation, which is called representation 2. This concludes this introductory part of our SIGGRAPH course, and we will continue with some Gallop web computing. Thanks a lot for your attention. Welcome everybody to my presentation, Gallop web computing with PGA. I would like to present Gallop script, our scripting language for Gallop and Gallop web. Then present some simple geometric object operations such as intersections. Then present some transformations and motions. And after that, two applications. One is to align two triangles in space, and the other one is dealing with kinematics and dynamics of a cube. Here you can see a table of Gallop script notations together with its meaning. In the first line, you can see how you can assign an algebraic expression to a multivector A. In the second, you can see the outer product of A and B. In the third line, you can see how you can comment one line or comment over some lines. In principle, this is the same as in C++. The question mark in front of a multivector means please explicitly compute this multivector. And as a note, at least one multivector of a Gallop script has to be marked this way. The colon in front of A means please visualize multivector A. There's a possibility of the definition of arbitrary colors in RGB mode, and there are also predefined colors, for instance black, blue, cyan, and so on. Please remember the main representation of the geometric objects of 3D PGA. The plane is represented as a vector. It is described by the normal vector n minus d, means the distance to the origin, times E0. A line is a bivector and can be defined as the outer product of two planes. And the point is a trivector as the intersection of three planes. This is a very simple example of one plane. We define the plane pi based on the normal vector E2, means the normal vector in the y-axis direction, and with a distance to the origin of 0.25. And we say that we would like to see the pi visualized in yellow. This can be seen on the right side in the visualization window. And since we added the question mark in front of pi, we are interested in the code, in the computation for pi, and this function, in this case, this c function can be seen on the bottom as a function called script without any parameters, and we compute the multivector pi, which in principle is a 16-dimensional array, but only non-zero elements are shown, means only the plates E0 and E2, which are indicated by the comment, are computed in this function. The coefficient of E0 is minus 0.25 and the coefficient for E2 is 1. If we would like to visualize our plane with an arbitrary distance to the origin, then we can use a variable d, for instance, instead of a concrete value. And then Gallop Web is generating a slider with an interval between 0 and 1. And using the slider, we can change the distance to the origin, in this case, between 0 and 1. That's a simple example for the intersection of two planes. P1 is defined as E2 minus 0.2 times E0, means with distance to the origin of 0.2, and P2 is defined with a normal vector E1 and with a distance 0.6 to the origin, and P1 wedge P2 means that we intersect the two planes, and the resulting geometric object is the line L, and P1 is visualized in yellow, P2 in red, and the resulting line in green. If we use three planes and wedge them with the outer product, the result is the intersecting point of the three planes. And since the line L and the point P are indicated with a question mark in front in the Gallop script, their non-zero coefficients are computed in the generated C function. And we can see that L consists of 3 non-zero coefficients and P consists of 4 non-zero coefficients. What we have just seen is a meet operation of geometric objects, means the outer product means meet of two planes results in a line, or meet of three planes results in a point, and so on. And from the cheat sheet we know that there is also a join operation. A join operation in order to generate a line based on 2 points which have to be joined to one line, or join 3 points in order to get a plane, and so on. Means we also have this join operation, and this is the reason for alternative representation 2, which we will see in a minute, the join operation in principle is defined as the dual of the meet of the dual objects. Here we can see both representations. In the representation 2, the point is not a trivector as in the representation 1, but it's dual. And this point is then a linear combination of the basis vectors and can be computed as x times e1 plus y times e2 plus z times e3 plus e0. And the line can then expressed in the representation 2 as the outer product of P1 wedge P2, with both points being vectors and not trivectors. And the plane can be defined as the outer product of 3 points P1 wedge P2 wedge P3. And both of these representations are dual to each other. And for the visualization with Scallop web, the representation 2 has to be dualized before visualization. Here we can see how 2 points can be joined to one line in representation 2. P1 here is defined as 0.5 E1 plus 0.3 times E2 plus E0, and this means we realize that the x-coordinate is 0.5 and the y-coordinate is 0.3. And the second point is defined with y-coordinate of 0.2 and z-coordinate as minus 0.1. If we wedge them, they are joined to the line L, and if we would like to represent the points as well as the line, we have to transfer it to representation 1, means we have to dualize the points and the lines, and this is done in the visualization part of this Scallop script. Here we can see how 3 points can be joined to one plane, means the outer product of the 3 points represent the plane pi, and in the visualization part we see that we have a factor of 10 times f in front of the plane pi in the representation 1, and this is done because then we can play with the area of this plane, and this can be shown on the next slide. Here we can see the plane pi based on the scaling factor f, first with a scaling factor of 0.34, and then with a bigger one, f equals 0.63. Knowing that, it should be easy for you to make your own experience with joining a point and a line. If we compare the previously generated C code with the definition, for instance, of the point, we realize that P14 is -1, means the coefficient for E wedge E2 wedge E3, or for short E1, 2, 3, is -1 instead of 1. and this means that some kind of normalization is needed. Normalization of an object means the division of the object with the norm of the object, and the norm normally is defined as the square root of the inner product of the object with the reverse object. Here's a Gallop example for normalization. We define the plane pi based on the normal vector with arbitrary coordinates n1, n2, and n3, and with d as a distance to the origin. And then we compute the norm of this plane by the square root of the plane inner product reverse of the plane, and the generated C code, for instance, is a function with parameters n1, n2, and n3, means with the coordinates of the normal vector, but without the distance, means this function is independent of the distance d. And if we look at the computation, we see that in principle the length of the 3D normal vector n1, n2, n3 is computed. Means in the case of a plane, the normalization means that we have to divide by the length of the normal vector. Also, transformations and motions are described in the cheat sheet. So, for instance, the rotation with an angle alpha around a line LE can be simply expressed with the operator cosine half of alpha plus sine half of alpha times LE, means this rotation line. And for instance, a motor as the transformation of rotation and translation together between two lines LE and L2 can be expressed as a square root of the product of the normalized lines, or simpler as 1 plus the product of the two normalized lines, and this expression normalized. The composition of two motors M1 and M2 is simply the geometric product of them. Normalization of a motor is the same as the normalization, for instance, of a line. The reflection of a geometric object X in plane P can be simply expressed as a sandwich product P times X times P, and a general transformation of an object X with motor M can be expressed based on M times X times reverse of M. This means if we have two normalized planes, the transformation between these two planes can be simply expressed as a sum 1 plus the geometric product of the two planes. And then, for instance, we can linearly interpolate between the two planes based on this transformation. And if we look at the result of Gallop, the optimized source code, in this case C code, we see that a function is generated with parameter t, the linear interpolation parameter, and the computations are very, very easy, dependent on this parameter t. Since this interpolation parameter t is not a fixed value for Gallop, Scallop Web offers a slider for this parameter t, and selecting the values from 0 to 1 let us interpolate from one plane to the other. Let us extend this to the alignment and the interpolation of triangles now. The algorithm is based on the document A Guided Tour to the Plane-Based Geometric Algebra PGA by Leo Dorst, and his algorithm for the reconstruction of a motor from exact point correspondences in section 6.8 of his tutorial. We need a specific functionality, the exponentiation for this algorithm, and this can be done in Gallop with the definition of a so-called macro, and you can see approx this macro is defined with one parameter with a multivector. This has to be called underscore p1 for the first parameter. With additional parameters, they have to be called underscore p2 and so on. And in principle, the exponentiation is computed based on the development of a Taylor series. The motor between 2 points, 2 lines, or planes can be computed always in the same way. This is why we also define a macro called motor computing this motion. We compute this motion based on the division of the two objects, since we can avoid the normalization of the objects in this way. Then we have to normalize the resulting expression 1 plus P1 divided by P2. And this is always the result for the motion, whether it is 2 points, whether there are 2 lines, or whether there are 2 planes. We first compute the original points A1, B1, and C1 with arbitrary coordinates. Then, for this example, we compute a rotation based on the exponentiation of a rotation line and take this transformation in order to transform all the 3 points to the target points called AT, BT, and CT. The corresponding triangles A1, B1, C1 and AT, BT, CT can be simply defined for the visualization with a Ragma triangles with a list of these 2 triangles. In order to align the 2 triangles, in a first step, we apply the motor functionality to the points A1 and AT. The result is the motor transforming A1 to AT called VA. If we apply this motor to all the points A1, B1, C1, the result is the green triangle with A2, B2, and C2. For the next alignment step, we consider the lines going from AT to B2 and the line from AT to BT, call them L1 and L2, and compute the motor in order to transform one line to the other, and then compute the points B3 and C3 based on this motor VB, and then we can see the result in the bottom picture, and here we can see that the lines are aligned to each other. In the last alignment step, we have to transform the green triangle to the target triangle, and for that we compute the two planes the green triangle is lying in and the target triangle is lying in, and then again compute the motor between these two planes. The result is the motor VC, and now we know that for the complete transformation from A1, B1, C1 to the target triangle, we need all these transformations of each step together. Means we have to multiply VC times VB times VA, and the result is the complete transformation V from the original triangle to the target triangle. Again, we can compute the interpolation motor starting from 1 and ending at the complete transformation V with a interpolation parameter T, and we can apply this motor, this interpolation motor, to all the points A1, B1, C1, and the result are the points for the interpolated triangle. The pragma triangles now visualizes three triangles: the original, the interpolated, and the target triangle. And since the parameter T is arbitrary parameter and without any fixed value, Gallup Web offers again a slider for T for the interval between 0 and 1. In order to better understand projective geometric algebra, I can recommend to see the PGA tutorial of the SIGGRAPH 2021 by Leo Dorst and Stephen de Koenig. They explain the 2D PGA based on the 3D model with coordinates E1, E2, and the third one E0. And on the top of the slide you can see the two representations for 2D PGA. In representation 1, the line is simply represented by the 2D normal vector with coordinates n1 and n2, and the distance to the origin d. In principle the same as in 3D PGA with the planes, and the point is represented as the outer product of two lines. The representation 2 starts with a point as a vector with a point represented by its coordinates x and y, simply is represented in 2D PGA as x times E1 plus y times E2 plus E0, and the line in this representation can be expressed as the outer product of 2 points. Let's come now to the topic of kinematics and dynamics and how we can handle it with PGA. We will focus on an example with a cube and with spring and gravity forces. This is described in the PGA tutorial SIGGRAPH 2021 with the mentioned link, and you can also see it in the Gancha workshop with a second link on this slide. And our main goal now is to write a Gallop script in order to get optimized code for various programming languages for the solver to solve this animation problem. This is a general model how physics is modeled in PGA. In principle, all the physical parameters are described by PGA lines, and all the physical parameters combine both rotational and translational parts. As with motors, a motor is a combination of rotation and translation. In the same way, fork is a combination of force and torque, and means also combining rotational and translational forces. The same, for instance, for velocity, rotational and translational velocity combined in one expression. And in the left bottom part of the picture, you see the differential equation, which we use in our example as follows. So this is the core formula for dealing with dynamics in PGA. It reads the dual of the time derivative of the velocity equals to the fork, combining force and torque, minus the regressive product of the dual velocity and the velocity, and the time derivative of the motor for the transformation rigid body motion equals to minus half motor times velocity. As I already said, all the physical parameters include both rotational and translational parts, and the cross is the regressive product. And as follows, we will use the notation B instead of V because it is also used in the Gancha example. This is the solver part of the Gancha dynamics example, a bit adapted to a Gallop script. M and B are the parameters for motor and the velocity. dm and db are the derivatives of m and b. A rate is needed for the simple Euler integration scheme that we are using in order to solve the equation that we just saw. The core computation of this dynamics example is to compute the next motor and the next velocity in this Euler scheme, and this is done here based on two Gallop macros solving this equation of motion. And the C code generated by Gallop for this example is looking like this. It is a C function with parameters p1, p2, p3 for the velocity, and with the parameters m0, m1, m2, m3 for the motor, and also the rate can be used as a parameter. And then the computations are very simple for the for all of the coefficients, means the 4 coefficients of the motor and the 3 for the next velocity step. This example is without forces, but it can be simply extended to forces, and with this very simple code I would like to conclude my presentation and would like to thank you for your attention.
Hey everybody, I'm back. I'm going to talk about a special structure within geometric algebra. We call this structure the conformal geometric algebra. So first of all, let's step back and think about problems with our real n-space, Euclidean n-space. First of all, algebraically, it has a unique origin. Every number in n-space I can divide with except for 0. It also has, if you look at it very general, a problem with the point at infinity. We can't really do anything algebraically with the point at infinity. So we view these as problematic. You know from computer graphics how to get rid of the problem with the origin, right? You take the origin, you embed that in a space of one dimension higher, and then you displace the origin, usually along that vector, that unit vector. And then you work in that space higher. It's called affine space. And for like three-dimensional rotations, you use a four-dimensional matrix to work in that space. That's four-dimensional because you're working in a space higher. Well, maybe we can do the same thing with the point of infinity in a higher dimension. Well, what is the point in infinity? We can't displace it because it's not a vector, at least not in our geometric algebra or our Euclidean spaces. But we're going to solve that problem with a very special vector. So we'll look at this. To start with, let's just consider the hyperplane, the plane that we want to define and remove through the origin. So a hyperplane, we're going to take this point in n+1, and we're going to define it with two very special vectors E. Typically, you would see the definition of a plane with the normal n and the displacement vector d here. But we're going to call it E and E naught. And you're going to find out why in a second. So E naught takes this plane and it displaces it along parallel to the vector E. This is how we're going to define this new hyperplane. So what are these vectors E and E naught? They are going to be null vectors. This is probably a new term for many of you. A null vector is a vector which is non-zero but has length 0. Its square is 0. So if I look at the vectors in Rn+1, and I look at all of those vectors that are equal to 0 in their square, knowing that E naught and E are null vectors, I'm going to get a cone. This is the combination of all vectors E naught and E, which will have square equal to 0. So what is a null vector? One way to think of that as a metaphor is to take a rope, a certain length of rope. If it were a vector, it would have a particular direction. So I can pull on that rope. The harder I pull, the longer the length of that rope is. What if I pull in both directions equally? So I have a length of rope, but the force on that rope is 0. That's one way to think of a null vector. Physicists use this in space-time algebra to define the light cone. Some of you may be familiar with that as well. Otherwise, just accept it. It's a non-zero vector with length 0, with a square of 0. It's a mathematical construct. We're going to play with it. So there's our null vector. Now, if we take that null vector and we intersect it with that plane that we define using these two null vectors E and E naught, we're going to find a new structure called the horosphere. So N, defined by the vector E with the dimension little n. It is, of course, the intersection of this cone with the intersection of this hyperplane. You're going to get a parabola if your Euclidean space is two-dimensional, or in general a paraboloid. We're intersecting a plane with a cone, right? It's a conic. Now, very importantly, the function, the mapping that does this intersection, it realizes the mapping from Euclidean space to the horosphere looks like this. X is a point in Euclidean space. We're going to add to that point, this is the displacement, right? X squared times E divided by 2. This is a scaling factor. So we're displacing with the null vector, but we're displacing it as not as a linear map, but as a quadratic map. And then we displace it again with the vector E naught. This is like our affine space where we're displaced by a unit vector in a dimension higher. Well, we can show as x goes to infinity, right, all these other terms are going to become insignificant. And the only term that we're left representing the point in infinity is this vector E. So we have this unit null vector E, which has become our representative of the point and infinity. And it works algebraically within our system, even though it is a point at infinity. Other things we can prove now that we have this mapping is that between our Euclidean space and our horosphere, we have a bijective map. That parabola is bijective. In general, it is a paraboloid. The horosphere is a term that Gauss's student Wachter came up with. So it's existed a long time as a piece of geometry. But of course, Wachter did not have the power of the geometric algebra laid on top of it. One very interesting thing about this horosphere is that spheres and hyperplanes are points on this special hyperplane P n plus 1. And in fact, these spheres on the horosphere itself are just points. That is, they are spheres of radius 0. And as I move off the horosphere on that hyperplane, I get spheres with radius that are non-zero. The farther off the horosphere I go, the larger that radius is. And then as I have pointed out, that null vector E is my point at infinity. Furthermore, taking 2 points in Euclidean space, I can show that their distance squared, the negative of their distance squared, is just a proportion to x dot y on the horosphere. In other words, we have come up with a way of measuring distance using the dot product. This is a true distance geometry, something that mathematicians like Laguerre and others have been searching for in history. That means that Euclidean space and our horosphere are isometric to one another. Another thing that is very interesting is that the line segment A to B, written on the horosphere as our point at infinity wedged with A and B. This is how we represent a line segment, a limited segment, on the horosphere. Very convenient form. First of all, one of the immediate results is if I square that using the geometric product, I get A minus B squared. So it's just the length squared of my line segment A and B. This works for triangles too. E wedge A, wedge B, wedge C squared is the area of my triangle, and so forth. For any simplex, E wedge, A wedge, B wedge, C wedge, D wedge, and so forth will give me the volume of that simplex. Very sweet. So, conformal maps. Why do we call this conformal geometric algebra? Recall that a conformal map is locally isotropic. That is, any map which is conformal will take a small area around any point and scale it equally in all directions. This is very useful in computed fluid dynamics, for instance. When we have an equal pressure liquid, it's going to map into different shapes conformally, that is, isotropically. We see that here. It's a jet nozzle. The fluid is going to flow through that jet nozzle under pressure if it's an ideal fluid, and it will be isotropic. So in fluid dynamics, conformal maps are ubiquitous. We like it in computer graphics, like finite elements. We like these to try and keep these meshes as we morph them around to keep them isotropic. Likewise, texturing, we don't like local distortions when we map our textures around. And equal parameter steps, time steps. So for animation, for instance, we don't like those sudden jerks time-wise. All of this conformal maps. Now, Lievu proved a very important theorem about conformal transformations in Euclidean space where n is greater than 2. And that is that any conformal transformation can be expressed as a composition of reflections about a hyperplane. So if I want to reflect that about a hyperplane, or inversions about a sphere. So if I take a line segment, actually a line, and invert it about a sphere, I get a circle. Those two transformations and all of their compositions give me conformal transformations. We're going to use this fact to show how transformations, conformal transformations in the horosphere give us a very special result. Okay, in geometric algebra, a reflection, as we saw earlier, take a normal vector to a plane, take my variable, multiply it, do the sandwich operation, right? Minus n, x n. That will give me a reflection. It gives me a reflection around any hyperplane at the origin. To get a reflection around a general plane, I'm going to add to that 2 times that normal times the displacement of that plane away from the origin. General reflection about a hyperplane. It's linear, easy to compute in geometric algebra. The inversion in geometric algebra, I will take r squared, where r is the radius, and divide that by my variable x. This is any Clifford element. Subtract from that the center, and then I'm going to add to that the center again. And this gives me a general inversion about a general sphere in geometric algebra. If we map this using that special mapping I showed you earlier to the horosphere, we find out that we can do reflections on the horosphere during the sandwich operation with r as a bivector. We're going to take the normal and just add to that the displacement. We don't need the sandwich vector yet. The inversion, even more importantly, is the center minus r squared times that point at infinity divided by 2. This is a linear map. We no longer have a division a division by our variable. Remember from Levy that all other conformal maps can be computed by composition of these two maps. For example, the translation is just two reflections, two of these. So we can use this fact to linearize affine maps and the conformal group on the horosphere. So in general, a mapping G of X will be R inverse, or R reverse if we have called it, times my point times R. So that sandwich operator again, where R is just A times B for any two vectors, A and B. The reversion again is that rotor such that R reversion equals 1. Okay, compositions are easy. They're just repeated use of that sandwich operator. And this should be a 2, right? You're sharp enough to see that. So I'm going to take R2 times R1, 2 rotors, rotate twice, times my vector X, and then R reversion 1, R reversion 2. And I have composed two conformal maps. Any conformal map on the horosphere. Here's a simple example. And I take, say n is 3. So I'm in 3 dimensions. I'm going to go to n plus 2, 5 dimensions. Pick 5 points in 5 dimensions. In 3 dimensions. So 5 points, 3 dimensions. Another 5 points in 3 dimensions. So they span my 3-dimensional space. And I want to create a map that takes these 5 points to these 5 points conformally. Well, I know there exists a conformal map, and that means I have a scalar, lambda, such that that conformal map of these 5 points at those points can be written as that scalar lambda times these 5 points. I can dot these A's together and know that that will be equal to the B's times the lambdas dotted together. So I've set up a system of linear equations, which I can solve for the lambdas. Now that tells me I have a conformal map between these 5 points and these 5 points. They will map exactly to these 5 points, and the whole of space will map conformally. So I can use these mappings of points as control vectors to define my entire mapping of space. I've always thought this would be valuable. Wanted to come up with some kind of modeler that would allow me to do this conformal mapping. Maybe somebody out there will do that for us, or maybe I'll do it yet. Anyway, that's our quick introduction to conformal geometric algebra. Dietmar is going to give you some more examples and deepen your understanding by using Gallup in conformal geometric algebra. Thank you.
Welcome everybody to my presentation, Gallup Web Computing with CGA, or Conformal Geometric Algebra. I would like first to talk about compass ruler algebra, which is the 2D version of conformal geometric algebra, and about its visualizations with Gallup. In principle, it can be the same with Gallup Web. And then we will see how easy it is to extend from 2D to 3D. And I will talk about the properties of conformal geometric algebra and some examples for visualizations with Gallup Web. This topic refers to 3 books of mine. Foundations of Geometric Algebra Computing is focusing on CGA itself, with some examples for fitting of planes or spheres in point clouds, or inverse kinematics, robot grasping, computer animation, collision detection, or molecular dynamics. Introduction of geometric algebra computing is focusing on the compass ruler algebra, the 2D version of CGA, and is handling the objects, the intersections, transformations, and angles and distances. And as applications, it describes robot kinematics, detection of circles and lines in images, and robotic snake control application. The book Power of Geometric Algebra Computing is focusing on the new online version of Gallop called Gallop Web. Some of the examples in this book are considerations about runtime performance for C, or the description of the online connection for Python. Applications are molecular distance application for Mathematica, and for instance, the robotic kinematics for MATLAB. Let's start with compass ruler algebra. It consists of 4 basis vectors, E1 and E2, for the x and y coordinate. Then we have 2 additional basis vectors. One is E0, describing the origin, and the other one is E infinity, for the point at infinity. With 4 basis vectors, we have 2 to the power of 4 basis plates of compass ruler algebra, means 16 basis plates, 1 for the scalar 4 basis vectors, 6 bivectors as the outer product of basis vectors, then 4 trivectors and 1 pseudoscalar. The main geometric objects of compass ruler algebra are point, circle, line, and point pair. They have 2 representations. One is called the IPNS representation, the other one is the OPNS representation. A point with 2D coordinates x1 and x2 can be expressed as a linear combination of x1 times e1 plus x2 times e2, and for the 2 additional basis vectors e infinity, the coefficient is half x1 square plus x2 square, and the coefficient for e0, representing the origin, is 1. A circle can then be represented based on the center point P minus half radius squared times E infinity. This means this is a circle with center point P and with radius R then. And a line can be described based on the 2D normal vector plus the distance to the origin d times E infinity, and the point pair can be represented in this IPNS representation as the intersection of 2 circles, which is shown in the left picture. The intersection of the 2 circles are the 2 points that we can see, and in this example we will see it later. We make a line through these 2 points. Regarding the openness representation, the circle can be represented based on the outer product of 3 points, which is shown in the right picture. We have these red points, and the outer product of these red points are the circle going through these points. A line, in principle, it is the same. It is the outer product of 2 points with a point at infinity, and a point pair in this openness representation simply is the outer product of 2 points. And what is also important about IPNS and OPNS representation is that both are dual to each other. Means if we have an object in the openness representation, dualizing it is the representation in the IPNS representation. The meaning of the products of compass ruler algebra in principle is the same as also in the 3D conformal geometric algebra. The outer product means, for instance, the generation of geometric objects, or can be used for the intersection of geometric objects. The inner product can be used for the distance of point and point, the distance of point and line, the angle between line, and for instance, the distance of a point to a circle. And the geometric product is used for transformations, for rotations, translations, as well as for reflections and inversions. So for instance, the center of a circle can be simply expressed as the inversion of infinity. In Gallup, we have two alternatives to describe a point. First is the formula that we just saw as the linear combination of the 4 basis vectors. And the alternative is to use the predefined function create point with the 2 parameters x1 and x2. This is a Gallup script in order to compute a circle and visualize it. We describe the points P1, P2, and P3 based on the predefined function create point. And then we compute the outer product of these 3 points, dualize them, because this is important in order to have the IPNS representation for the visualization. As we already know, the line can be described based on the normal vector and the distance to the origin. First, we define the coefficients n1 and n2 of the normal vector. The normal vector then is a linear combination n1 times e1 plus n2 times e2. The distance to the origin d should be 2, and then the line can be defined as n plus d times e infinity. This is an example for a point pair as the intersection of 2 circles. C1, for instance, is a circle with a center point at the origin and radius r1 or 1. And C2, a translated circle in the y direction, and the point pair is the intersection of both circles described by the outer product of C1 and C2. With this information, it is very easy to compute the perpendicular bisector of a line segment. The line segment in this example is defined by 2 points, P1 and P2, the red points in the picture. And then we compute 2 circles around P1 and P2 with the same radius. And then we intersect the 2 circles based on the outer product of the circles. And then we have the dual outer product of the 2 intersecting points, means the line can be simply computed as the dual point pair, wedge E infinity. And if we dualize that, we are in the IPNS representation, which we need for the visualization of the line, which is green in the picture. Okay, let's extend everything now to 3D, to the conformal geometric algebra. This algebra now is based on 5 basis vectors. We have E1, E2, and E3 for the x, y, and z coordinate, and again E0 for the origin and E infinity for the point at infinity. With these 5 basis vectors, the conformal geometric algebra consists of 2 to the power of 5, means 32 basis plates, 1 scalar, 5 vectors, 10 bivectors, 10 trivectors, 5 quadvectors, and 1 pseudoscalar. And again, many of the plates have a geometric meaning. For instance, we will see that vectors describe geometric objects like points, spheres, and planes. And the bivectors represent circles and lines in space. In the picture, you can also see IJK means the complex units of quaternions, means with this 3 basis plates it's able to describe rotations, which we normally describe based on rotation matrices. Here you can see how easy it is to extend geometric objects from 2D to 3D. The expressions for a sphere and for a plane are in principle the same as the descriptions of circle and line in 2D in compass ruler algebra. And in principle, a plane is one specific sphere. It is a sphere with infinite radius, and you can imagine that if you look at the picture on the right and extend the point P to infinity and adapt the radius accordingly, at the end the result is the blue plane. And again, if you have A and B as 2 spheres, the outer product A wedge B describes the intersection of the spheres, means they represent a circle. And if we have a sphere and a line, their outer product simply describes a point pair which is the intersection of sphere and line. A circle can simply be described by the outer product of 3 points of this circle, means the outer product A wedge B wedge C describes the circle going through these 3 points. And if we exchange the point C, for instance, with E infinity, the result is simply the line going through A and B. And if we have a line going through the origin, the expression e to the power of minus half of an angle times L describes the so-called rotor, means an operator for the rotation around this line with angle phi. In principle, this is the same as a quaternion. And if the line is not going through the origin, means if it is arbitrary, this is also not a problem. The same expression e to the power of phi half times this line describes already a rotation about this arbitrary axis in space. And maybe you know that as dual quaternions. Here you can see a screenshot of Gallup Web for the intersection of line and sphere. In the area code to optimize, we define our sphere based on center point minus half radius squared times E infinity. Then we create the points O and L, compute the line based on these 2 points and the outer product with E infinity. Dualize that for having everything in the IPNS representation, and then we intersect our line with a sphere. The result is a point pair, and what's interesting is that if we use the inner product, PP means point pair times point pair, the result is a scalar describing whether the line is intersecting in reality the sphere or not. In the area where variable assignments only for the visualization, some variables are defined, and in multivectors to be visualized, the color of the object to be visualized is defined. And this means, for instance, the line is green, the sphere is yellow, and the point pair is blue. This visualization can be seen on this screenshot together with the Python function computing this parameter has intersection, describing whether the line and the sphere really intersect. Here we have another example. It defines a sphere based on 4 points, which are on the sphere. We define the points P1, P2, P3, and P4, and the resulting sphere in OPNS representation is simply the outer product of these 4 points. If we are interested in the center of the sphere, which we just computed, we can normalize the sphere S, resulting in a linear combination of E1, E2, E3, E0, and E infinity. And the E1, E2, E3 component in principle describes this center as in the 3D coordinates. For a better runtime performance, there is a pragma which is defining which coefficients should be computed by this resulting point C. And in this case, we say, okay, we are only interested in E1, E2, and E3. And the coefficients for E0 and E infinity do not have to be computed. Thanks a lot for your attention. Welcome everybody to my presentation, Computing with Conics and Quadrics. It refers to my book, The Power of Geometric Algebra Computing, which was published this year. One part of the book is about arbitrary geometric algebras with 3 examples. One is about Gallup Web for conics, means for ellipses, parabolas, and hyperbolas. Then about the double conformal geometric algebra, which is able to handle quadrics, but also toroids and cyclides, and about the geometric algebra for cubics, dealing with cubic curves and surfaces. You are able to define your own geometric algebra in Gallup. There is no fixed limit for the dimension of the algebra, but since the multivector of an n-dimensional geometric algebra is already 2 to the power of n dimensional, there is a limitation of memory of your computer. It means depends on the memory which algebras you can define. With Gallup, there is a support of predefined multiplication tables you can define, and also on-the-fly computation is possible with different benefits, and there is a support of 2D and 3D visualization. The only thing you have to do to define your own algebra is to integrate two files in a specific directory, and that's it. Our first example is a geometric algebra for conics, or GAC for short. It is described in chapter 10 of my book, The Power of Geometric Algebra Computing, and it is an 8-dimensional geometric algebra for dealing with ellipses, circles, hyperbolas, parabolas. And here's an example for the intersection of an ellipse with a circle. Since the formula for the geometric objects in this algebra are a bit complicated, they are predefined. The ellipse, for instance, can be defined based on the two semi-axes in this example. One is 1.5 and the other one is 0.8. Also, points can be defined with a function create point. It's the same in 3D. This is why the z coordinate is always 0 for 2D application. And if, for instance, the 3 points of the picture are defined, the red, the blue, and the green, based on the inner product, you are able to decide very easy whether this point is outside, inside, or on the ellipse. Geometric objects of this geometric algebra can also be described based on 5 points and their outer product. Here in this example, we define the points P1, P2, P3, P4, and P5, compute the outer product, and the result is an ellipse. In order to visualize this ellipse, we have to dualize, and in this algebra we have 2 operations for dualization, depending on whether we would like to dualize from the outer product null space to the inner product null space, or vice versa. In this example, the outer product of the 5 points are the outer product null space representation, and this is why we need the function dual OI for OPNS to IPNS in order to visualize this conic. Also, transformations can be handled very easy in this geometric algebra. In this example, we have the blue ellipse. It is defined based on the two semi-axes 0.2 and 0.5. and we would like to translate and rotate this ellipse. This can be done also with predefined functionality. For translations, for instance, we have a function for the translation in x direction and one for the translation in y direction. Txe is the basic ellipse translated in x direction with 0.5. The operations are always described based on a sandwich product, means we have to multiply with this translator from the left and from the right, with a reverse translator, and txye, for instance, is the translation of this just translated ellipse in y direction with 0.1. Also the same with the multiplication from left and right. Also for the rotation we have a predefined functionality. It is called rotor, and you can define the angle. In this example, it is a rotation with an angle of 45 degrees, and again we have to multiply from the left with the rotor and from the right with the reverse rotor. If we would like to visualize it with Gallop, we have to consider that because of internal issues of Gallop Web, we have to decide for a scaling factor for the line widths of our visualizations. And in this example, we decided to use 100 as a scaling factor. It depends on you what scaling factor you like, and sometimes you have to play around with the scaling factor in order to get good visualizations. As usual, intersections can be defined based on the outer product, and in this example there is the intersection of an ellipse with semi-axis 1.5 and 0.6 with a circle with center point 0, 0 and an arbitrary radius, and the intersection as the outer product E wedge C. Let's come to the double conformal geometric algebra. It is a 10-dimensional algebra for quadrics and also for toroids and cycloids, and it is described in chapter 11 of my book, The Power of Geometric Algebra Computing. In this example, we can see how we can define spheres, ellipsoids, and toroids in this geometric algebra, and they are visualized in red, magenta, and blue based on the 3D visualizer of Gallop. Again, transformations can be described also with predefined functionality. In this case, we are using a rotor, a dilator, and a translator in order to rotate, dilate, and translate an ellipsoid. And again, the visualization is based on the 3D visualizer of Gallop. Again, intersections can be expressed based on the outer product of geometric objects. In this case, we can see the intersection of different types of cylinders with a plane, a normal cylinder, a parabolic cylinder, and a hyperbolic cylinder. And the result are ellipses, parabolas, and hyperbolas. Thanks for your attention.